You know, what's the last thing you did on your computer? I bet it started with a click. It seems so simple, right? It's the most basic thing we do. But in that tiny fraction of a second, this silent, incredibly fast conversation kicks off inside your machine. Today, we're going to listen in on that conversation. We're going to trace the amazing journey of just one single click.
I mean, really, think about it. It feels totally instant. You click, something happens. And because it's so seamless, we just assume it's, well, kind of like magic. But what's actually going on in that blink of an eye? How does that signal get from your finger all the way to the pixels lighting up on your screen?
Well, it's definitely not magic. It's something way more interesting. It's a perfectly choreographed dance between all the physical hardware and the invisible software, and we're going to follow our click through every single step of this dance. By the end of this, you're going to know exactly who's leading, who's following, and the silent language they're all speaking.
Okay, so our clicks journey has to start somewhere, and it starts at the very heart of the operation, the computer's thinking core. And to really get what's happening here, you need to meet the two main characters in our story. You've got the brain, and you've got its incredibly fast workspace.
So first up, meet the Central Processing Unit, or as we all know it, the CPU. This is, without a doubt, the brain of your computer. It's this incredibly complex chip, basically a tiny city of microscopic circuits. And it's where all the heavy lifting, all the actual thinking gets done. It's the part that turns abstract commands into the real actions you see happening.
Now, this brain isn't just thinking randomly. Oh no, it operates on this relentless three-step rhythm. First, it fetches an instruction, kind of like a chef grabbing the next step in a recipe. Then, it decodes it, figuring out exactly what it means. And finally, it executes the command. Now, try to imagine doing that entire sequence billions of times every single second. That's the mind-blowing speed we're talking about with a modern CPU.
But you know, even the fastest brain in the world is pretty useless if it doesn't have a place to work. It can't hold every single thought in its head at once, and that's where RAM, random access memory, comes into the picture. You should think of RAM as the CPU's workbench. It's a super fast, temporary holding area for all the tools and data for whatever job it's focused on right now.
So, this is it. This is the fundamental partnership that powers your computer. The CPU is the master craftsman, doing all the complex work, and the RAM is its workshop, keeping every single tool and piece of material it needs right there, within arm's reach. See, if the workbench is too small, the craftsman is always stopping to go find things. But a bigger workbench, more RAM, means it can work on multiple, complex projects all at the same time, totally seamlessly.
Okay, so we've got a brain and we've got a workspace. Great. But how do they talk to each other? How does a signal from your mouse even get to the CPU in the first place? Well, for that, the computer needs a central nervous system.
And that nervous system is the motherboard. If you imagine the computer as this bustling city, then the motherboard is the entire network of roads, highways, and tunnels. It's the big physical circuit board that everything, and I mean everything, plugs into, creating all the pathways for data and power to flow between the CPU, the RAM, and every other part of your machine.
And it really is this central hub of connections. You've got these specific, dedicated slots for the super important stuff, like the CPU and the RAM, but then you also have expansion slots for adding new things, like a beefy graphics card. And to manage all this traffic, the motherboard has its own little traffic controllers, specialized chips that direct the flow of data, making sure a signal from your mouse doesn't cause a traffic jam with data that's heading to your speakers.
So we have all the physical pieces, right? The brain, the workbench, the nervous system. But hardware by itself is just silent, useless metal and silicon. There's a huge piece missing, an invisible conductor that brings this entire orchestra to life. This is the real ghost in the machine, the software that translates your click into a language the hardware can actually understand.
That conductor has a name. It's called the kernel. It is the absolute heart of your operating system. Whether that's Windows, Mac OS, or Linux, they all have one. The kernel is the ultimate translator. It's the bridge between the world of software you see and the world of hardware we've been talking about. And it's so important that it lives in its own protected space and memory, where no other program can mess with it. It is always running.
Think of the kernel as the ultimate manager of the whole computer. It's strict, but it's fair. When your click signal arrives, the kernel is the one that answers the phone. It looks at all the different programs that are screaming for attention and decides, okay, you get to use the CPU now, but only for a millisecond. It manages all the memory, kind of like a librarian for the RAM, making sure no program scribbles all over another program's work. And what's really fascinating is that not all kernels are built the same way. There are really two main design philosophies. On one hand, you have the monolithic kernel, where all the main operating system services live together in one big, efficient block. This setup is super fast and powerful, but the risk, if one tiny part has a bug, it can bring the whole system down. On the other hand, you have the microkernel approach, which is way more modular. Only the absolute essentials are in the core, and everything else runs as a separate process. It might be a tiny bit slower, but it's much more resilient. If one part fails, it won't cause a total system meltdown.
All right, we have officially met all the players in our orchestra: the mouse, the motherboard, the kernel, the CPU, and the RAM. So now, let's put it all together. Let's follow our one simple click on its incredible lightning-fast journey through this entire system.
So it all begins with that physical touch. Your finger presses the button. An electrical signal instantly races down the wire to the motherboard. The kernel, which is always watching, picks up that signal, recognizes it as a request to launch a program, and shoves it into the line for the CPU. In the very next nanosecond, the CPU grabs the program's code from its workbench, the RAM, and just starts executing the instructions, one after another. And literally, before you've even lifted your finger off the mouse, the result of that entire chain reaction is already appearing on your screen.
And that's really the secret, isn't it? That's the key to this whole thing. That single click is only possible because that unseen conductor, the kernel, is always there, facilitating this constant, ridiculously high-speed interaction between the physical world of hardware and the invisible world of software.
So the next time you click, just take a half second and remember what you're really doing. You're not just clicking a button. You're kicking off an incredibly complex conversation inside this amazing symphony of components. And you're the conductor. So the only question is, what are you going to conduct next?